My name is Larry Crosby. I'm an 18-year veteran with ADI. That included 15 years as an FAE in the base sales office in California. I've been in the electronics industry for over 40 years. I have an MSCE, and I've worked in the audio, ATE, computer, and medical device industries. So here's our agenda for today. We're going to do a brief overview. I've got a series of slides on getting started, and then some information on fundamentals. So with that, let's get going. This is session 1, Introduction to Power. We cover power fundamentals. Session 2, we'll cover converters, switching converters, LDOs, and switchers. And that's, the details are the different types of converters. We'll do some more expanded slides on LDOs. That will get us going into the whole power design realm. Session 3 is actually been split up into 2 sessions. So there's a session 3 and a session 4. And this talks about getting started and the various tools that are available in the ADI toolbox for helping you with power design. So we're here at session 1. Okay, so I wanted to give you a sense of the size and depth of this space in the electronics field. So I decided to look at how many power supplies do I have in my home. And so I went around and counted everything, and I have a home office, and we have something like 4 desktops in our home between myself and my wife. We have laptops, we have printers, and each of those has multiple power supplies inside it. So the desktop might have 10, the laptop 10, and the printer probably 10 as well. So that's 100 power supplies just for the home office. In our living room, there is some stereo equipment, a TV, miscellaneous video equipment, that's another 36. Cars these days have a lot of power supplies in them because of all the infotainment and navigation and engine control. So we have 3 cars, that's about 75 power supplies. And then there's a bunch of miscellaneous things like appliances. Appliances these days, they all have interfaces, and so they need power supplies to run those interfaces. We have battery-powered devices, and chargers for all those battery-powered devices. So overall, in my home, I figure we have about 400 power supplies, and this is just one home. So this gives you a sense of, why power is important. So all electronics require power. A small system may have just a few power rails, but a large system could have many. The input power sources are variable and they may have noise. And so we need to be able to address that. Signal chain is another example. Signal chain applications have strict power requirements. Okay, so where do we get started? The first place we generally start when we're doing a power design is to develop a power tree. And some of the benefits are that a power tree appeals to visual learners. Most engineers designing with visual applications, whether it's schematics or AutoCAD or whatever, having a power tree allows people to get their head around where's the power coming from, where's it going, how does that all work? And the input side is where we start. So we have to ask questions. What is your input power source? What does it look like? Is there one source or more than one? Is there redundant power? Some applications have redundant power supplies in case one dies or goes offline for some period of time. And we also have to consider the power path. How does the power get from the power source to the input to our circuit? And are there cables involved? All of that is important. And what is the input voltage range? In the legacy telecom industry, the nominal power source for the systems is 48 volts. But because these systems have battery backup. The banks of batteries that are used for that backup source have a wide range. They could be from 36 to 72 volts. So that's a really wide range. And we have to be able to accommodate that in our power design. Is the input source current limited? Virtually any input source is going to have some sort of limitation on how much current it can provide. But we need to understand what's that current limit level, including tolerance, and what does the power supply do when you hit current limit? Does it shut off? Does it brown out? In other words, the voltage droop? Does it go into hiccup mode where it shuts on and off and on and off, trying to restart? We need to understand that in order to design the power system appropriately. And just to give you a sense of how involved this can get, I'm going to show you an example about solar panel as an input. So solar panels have a unique power profile. And if they're the input for your system or your device, you need to understand how they operate so you can design the power systems appropriately. So here's the example. This is what's called the IV curve for a solar panel. The red line shows there's current on the vertical axis, voltage on the horizontal. And as we see, the red curve shows what the solar panel looks like as a function of that voltage and current. So now you need to remember, power is the product of voltage times current. So on this red curve, if we short out the output of a solar panel or solar cell, we'll still get current out of it, and it's the short circuit current at this upper left corner. That's the maximum current that the solar panel can deliver. But since there's no voltage across it because we've shorted it out, there's no power delivered. We're delivering current, but it's 0 volts. So then as the voltage is allowed to rise, eventually we get to this point down here in the lower right corner where we're drawing 0 current from the solar panel. And this is the maximum voltage point. So we have lots of voltage, but there's no current being drawn. And so again, the power delivered by the solar panel is 0. And so this blue curve is a continuous multiplication of the voltage at any point times the current. And you can see it rises up. And then right here, there's sort of a peak level. And so this is called the peak power point, or the maximum power point. And notice that that's not at the highest current level. The current has dropped a little bit, but we still have lots of voltage. And so that's why we get the peak power. When you design power supplies that are using a solar panel as the input, you have to make sure that the power supplies won't overload the solar cell, because you'll very quickly end up down here at the short circuit current with no voltage and nothing works. So that's just an example of why the input source needs to be understood in order to design appropriately. Power trees. Years ago, I used to use a drawing program called Visio to create power trees manually. So Visio is a sort of general purpose drawing tool. It's now part of the extended Microsoft Office suite. And this is an example of an actual power tree that I drew up. The input is 12 volts. That's what this system had available. And we have various output voltages. And I put some notes in here to indicate what these different rails were powering. And then in the boxes were the devices that I'd chosen to provide those power rails for the circuit. And this is pretty effective. It, shows the big picture of how the power is being distributed and how it's being generated by the different devices. But it's got limitations. It can't tell me what's the total power I need from a 12-volt input, for example. Many years later, ADI developed power tools to help us do the power design. And one of those tools is called LT Power Planner. It's both a graphical tool to create the power tree picture, if you will, but it also performs calculations on the fly, much like a spreadsheet does. In this example, we have a 24-volt input, and we have several power converters, and these loads, the pink boxes over here, are the different loads that the system has. So we have a 1-volt load that needs 3 amps, a 3.3-volt load that needs 2, etc. And you can see the numbers that are shown around these boxes. You can enter in the efficiency for each power converter, and the system calculates what's the input current that this converter needs in order to develop these two output rails. And then you can walk that back all the way to the input. And so here we can see that the 24-volt input has to be able to deliver a little over an amp of current. This is a more powerful tool. It provides the same graphical picture, but it also has some nice calculation features. And there's a little summary report that it can generate showing you the total power input, the total power output, the total efficiency, and that's for the whole system all rolled up. There's going to be more information on Power Planner and how to use it in session 3 of this training series. Okay, so let's talk about the power input path. Here is a simple diagram of what the power input path might look like. Power source I've modeled as just a voltage source, and the path from the power source to V out, this is the output of the power input block. This V out would go to our circuit and provide power for all the downstream rails. But we notice that we have to include parasitic resistance and inductance in this path. And I'll show you why in just a minute. So the connection between the power source and our circuit might be PCB traces, or it might be a cable. If you have a power adapter, which all of us have these days with our battery-powered devices, it's a little device that plugs into the wall outlet and then has a cable that you plug into your device. That cable has parasitic resistance and inductance, and we have to include that in our understanding of how the power input is going to react and how to make sure that we cover all those bases. So why does this matter? Well, if the input is hot plugged into our device, and hot plugging means connecting a live input voltage to some device or system when the system was initially unpowered. So this could be inserting a board into a chassis where the chassis is already on, or it could mean plugging your wall adapter into your phone or iPad or laptop. So when you make that plug-in connection, the plug is already live. And so what happens when we do that? Well, we have to look at we have to analyze that. So the capacitors on the input to our device initially are discharged. We make this hot connection, and there's a surge of current to fill up that empty capacitor. And that current surge can create overshoot. And we'll see why in just a minute. And so one mitigation, ceramic caps are commonly used for input filtering because they're small, they're relatively low cost, and they have very low series resistance, or ESR. But that can mean this current surge can be very high. So one way to mitigate some of that is to add what's called a lossy electrolytic cap in parallel with the ceramic cap. And we're going to take a look at that right now. So I'm going to switch over to LT Spice. LT Spice is a simulator developed by Linear Technology. And we can simulate what will happen and see the results. And we can do that without building anything, which is a real convenience. So here I have modeled our input source. I've used a pulse waveform to simulate what happens when we hot connect it. So the voltage is going to rise from 0 to 12 volts in 10 microseconds. And that's a reasonable time period for a hot plugged connection. And then I've got two circuits that are connected to this input rail. One has series resistance and inductance that simulate a cable, and just ceramic caps on our input. So we can look at what happens here at this node called out1 when we run this simulation and we get the fast rise time on the input. I've also added a second circuit where we have an electrolytic cap in parallel with the ceramic cap. And so we can look at both of these and see what happens when we do this hot plug operation. So let me run this. And then I'm going to just change this to look like that. So first, we're going to look at the input. So here's our input rising from 0 to 12 volts in 10 microseconds. Here's the voltage that'll appear on the output with just the ceramic cap in the picture. And as we can see, this voltage overshoots up to 20 volts. And then it bounces up and down, and many of you may recognize this as an underdamped response from your early circuit theory classes. So that ringing behavior decays slowly and eventually ends up settling at the 12-volt level. But the 20 volts could be a real problem. If your input supply is 12 volts, the downstream circuits might be rated for 16 volts or something like that. And under normal circumstances, that should be fine. But in this case, if you exceed that 16-volt rating, you could damage parts. Things could blow up. The other thing we should probably look at is, what does the current look like in this path when this is all going on? So we can probe the current through the resistor. The current is going to be the same through this resistor, R1, L1, and into the capacitor. So since that's in series, the current's the same everywhere. If we probe the current in R1, we can see what happens. And we see that it rises up, and it rises up to almost 90 amps. So there's a 90 amp current surge because it's trying to fill up this ceramic capacitor. And that may be a problem for your input supply. If your input supply is designed or specified to deliver 5 or 10 amps, if you try to draw 90 amps out of it, something's going to happen. And it may not be what you expect, or it may be unpredictable, or the power supply might just shut off. So none of that is good. So now let's look at what happens when we add a lossy electrolytic cap. And to explain what lossy means, I'm going to look at the specs for each of these caps. So the ceramic caps, there are two 22 microfarad ceramics. And notice their equivalent series resistance is 3 milliohms. It's 0.003 of an ohm. And that's why they work very well, because they have very little series resistance. But that's what gives rise to this huge surge in current. Now, if I put a 330 microfarad electrolytic in parallel, the cap that I've chosen for this position has an equivalent series resistance of 1/10 of an ohm, or 100 milliohms. So that's much larger than the series resistance of the ceramic cap. But it will provide some benefits. And let's take a look at that now. So here, I'm going to look at this second output. And now we see, oh, it only overshoots to 14 volts. So why is that? It's because the electrolytic capacitor, which is much larger than the ceramic cap in capacitance value, helps damp that ringing behavior. The ringing is caused because this is a classic series RLC circuit. And the Q of a resonant circuit like that has to do with the resistance. And since the resistance here is pretty low, 6 milliohms, that's why this circuit rings. This one, we have the series resistance, but then we also have 100 milliohms in the electrolytic cap. And so that higher resistance provides damping, and the damping reduces the overshoot, and it settles very quickly. Now, let's look at the current in this path. So the current here, it overshoots, it actually goes higher than the current up here, goes up to about 135 amps, but then it settles down more quickly and without all the ringing it settles down to 0 amps once these caps have charged up. So this isn't without, it's not a perfect solution. It's not without caveats, but it does address one problem, which is the overshoot. So this is why we need to understand what the input path looks like so that we don't get surprised when we build a board and things don't work when you do the hot plugging. So that's all I'm going to talk about for the input path, but I just wanted to let you know that we have dedicated control circuits that can help deal with these input path problems. And they can address both the current surge and the voltage overshoot. And these will be discussed more in phase 2 of this training when we do a deeper dive into the various types of power circuits. But just some examples of the types of circuits that will be covered. Ideal diode controllers. These are devices which are designed to handle redundant inputs. And so the basic way that redundant inputs were handled years ago was just to use a diode in series with each circuit, and you created what was called a diode OR circuit. At high power, the heat dissipated by the diode can be significant. So we have circuits that will act like a diode but have almost no voltage drop. So no voltage drop means no power dissipation. There are hot swap circuits, which are designed to mitigate both the current surge coming in and provide short circuit capability. And surge stopper circuits, which find lots of applications in automotive environments and other environments where the input might bounce around or go to a high value for a short period of time. Okay, so now we have to focus on the output rail requirements. So how many rails are there? You need to know the output voltage and current for each rail and the output ripple requirements. Ripple or steady state ripple is the variation that comes from, in most cases, from the switching power supplies that might be used to generate the different rails. So the ripple is a small up and down variation around the regulator's set point. And these are generally constant. They're just steady state little sinusoidal ripple that'll show up on an output rail. But there's also something called transient response. So the transient response is what happens when the load current changes suddenly. So you're powering a microprocessor and the microprocessor is idle. And so it's only drawing a few amps from the supply rail. But then the microprocessor gets a request. It says, oh, do all these calculations or run this program. And the microprocessor wakes up and starts executing commands, and the current goes quickly from a couple amps to maybe 10 amps. And when that happens, there'll be a deviation in the power supply until the converter that's providing that power settles. It settles at the new higher current level. So some circuits are sensitive to that. And an example is the latest CPU and FPGA core supplies. So the core is the thing that runs most of the internal logic on these large devices. And they often have pretty stringent ripple and transient response requirements. So these devices, and it'll be specified right in their data sheet, it might say the core supply has to stay within plus or minus 3% of its nominal value. And so on a 1-volt core, that's only 30 millivolts. That's a pretty small voltage. And we have to design the power supply to stay within that window under all circumstances. Because if it doesn't, if you go outside that 3% window, the manufacturer won't guarantee that the operation will continue as expected. So all bets are off, basically, if you exceed this window. So here's an example of a power supply design that I did, and it had that 30 millivolt restriction. And this is the transient response. So this is from one of the tools that we'll look at in a later session that shows the nominal voltage. And then right at this point here, the current steps up, the load current steps up. And when that happens, the supply voltage starts to fall because, for a brief instant, the power supply isn't aware that the current's changed. So the voltage dips down, and then eventually the power supply sort of realizes, oh, current went up, and it makes changes to the operation to provide the higher current. And so then it brings the voltage back up and it resettles to that nominal value. But so this area right here, this is the transient response. And there's a similar behavior when the current steps down. So we were running along at the beginning, maybe a couple amps. Here the current steps up to 5 amps, let's say. So there's this response. And then at this point over here, the current goes back down to that lower nominal voltage. And when that happens, the voltage will start to rise. And then the power supply says, oh, there's less current required, and makes changes so things settle down. So this peak to peak, that's the critical window that we have to look at. And we have to make sure that it stays within this 30 millivolt spec for this device that we're powering. And so we take a measurement, and sure enough, this is about a little over 20 millivolts in each direction. So we're well within that plus or minus 30 millivolt spec. And this supply will work well for this device. Some other circuits that are sensitive to noise and deviations are things like SerDes circuits. SerDes stands for serializer, deserializer. These are circuits that are used to eliminate the wide data bus that might be required. So you have a CPU, it has a 32-bit data bus internally on the chip. And if you don't want to burn 32 pins on the device to provide those 32 bits of output data, one way to mitigate that is to turn a 32-bit word into a serial progression of bits that only uses 1 or 2 pins. And so now instead of 32 pins, we only need 2. And the compromise is that the serial bit stream that represents that 32-bit word has to run at a much faster data rate in order to be able to effectively deliver 32 bits at a particular speed. So 32 bits running at a 1 megahertz rate, that means nominally there's a new 32-bit word every microsecond. If you serialize that, now the bit stream has to be at 32 megahertz in order to get all 32 bits out in the same 1 microsecond interval. So SerDes circuits are sensitive to the power supply rails because they're very high-speed circuits. And that's a common theme you'll see over and over again. High-speed devices are typically sensitive to what their power supplies are doing. Mixed signal power rails are also critical. So mixed signal devices like data converters, things like that, have a limited power supply rejection ratio. So the power rail for the ADC or DAC, if you have deviations or noise on that supply rail, they may come through to the output data and corrupt the performance of the device. So if you're spending $10, $15, $20 on a high performance ADC, and they can't get the full data sheet performance because the power rail is noisy, you're not going to be happy. And so we need to be aware of that so we can design the power system to have low enough noise that it won't adversely affect the performance of the data converter. And here's an example. This is the output from a high-speed data converter, and we see these little spurs here. These can be related to noise on the power supply rails. and these are generally undesirable. So power supply design, you've asked about the input, you've asked about the output voltage and current. Now you also have to ask about the priorities for their application. So things like the voltage and current are requirements. You need to have 1 volt, you need to have 1 volt at 10 amps. Those are requirements. Those are, minimum. We need at least these types of numbers. But the priorities are more subtle. So you need to rank these different characteristics in order of importance. So size, how much space does the power design take up on their PC board? Efficiency, how efficiently can the power converter convert from the 12 volt input to the 1 volt output? Noise and ripple requirements. These are small sort of steady state variations, and the transient response. And then finally, cost. So these are all different characteristics that will affect which power device we recommend and what the design actually looks like in terms of the other components that surround the power converter. So we gather the power requirements, input, output, and the other power requirements, and now we're ready to get started. So I'm going to take a little deviation here to talk about fundamentals, because this is critical things that you need to bear in mind when you're doing the power design. So most analog circuits can be broken down into pieces, which can be solved by fundamental circuit laws. And these circuit laws go back to, your first engineering courses. So Kirchhoff's current law, the sum of all currents entering a node must be 0. It's pretty straightforward, but nonetheless, you need to keep it in mind when you're doing design. So here's a schematic example. We have 3 resistors. We have 2 voltages and a 3rd voltage at the summing node here. And so these 3 currents have to add up to 0. And note the polarity is determined by the direction of the current flow. So here we're looking at this midpoint node. I1 and I3 are flowing into the node. I2 is flowing out. And that's why we have this equation here. So why is this important? So let's take an example. I need a power supply that I can adjust in my system automatically. So I need my CPU or whatever other intelligence I have to be able to adjust the output voltage of the power supply. Well, here's a straightforward way to do that. You have a regulator, and it has a feedback node, which is used to sense the output voltage. And you add a 3rd resistor and a DAC, and now the DAC can inject current into this and make the output go up or down. And that right there is Kirchhoff's current law in action. And you can solve it by it's a classic 3 equations, 3 unknowns algebra problem. It's solvable. And after doing this a half a dozen times myself for, different designs, it dawned on me that I don't like doing all this math and, filling up a notebook page with equations. Why don't I create a tool to do the arithmetic for me? And so I created this little calculator. And this is just an Excel spreadsheet. And it has, I have the little graphic that shows the DAC and the 3 resistors and the 3 currents. And then I input some data. So this value right here is the regulation feedback voltage. So that's the voltage that the power supply wants to have at that feedback pin when it's in regulation. And then I have some information about the DAC, the full scale voltage, the 0 scale, and the midpoint in between them. And then I enter in, what do I want the output voltage to be when the DAC is at full scale? And it's important to note that this feedback pin or feedback voltage, that's an inverting input. So if you pull up on the feedback node, the output goes down to compensate. If you pull down on the feedback node, the output goes up. So that's why these 3 values, with the DAC at full scale, we have the lowest voltage. With the DAC at 0 scale, we get the highest voltage. I want a 3.3 volt output, and I want it to be able to go from 3.1 to 3.5 volts. And the way I've set up this design tool or a calculator tool is there are values that I can enter in manually, and those are the blue cells. And then the yellow cells are calculated by the spreadsheet. There are equations behind these cells that are yellow. And so Excel does all the math for me. I included the currents at all three different states just for my information so I could sort of see what's going on. And I picked two values for R1 and R2. So R1 is the top resistor, R2 is the bottom. And the spreadsheet calculates a nominal for R3. And so I spent the time to create this calculator. Now I can get the answer in a minute, where before solving three equations and three unknowns might take 20 minutes, and I might make a mistake. You never know. So this is a much more expedient way to get the answer. And once it's debugged, it's right every time. Another fundamental law is Kirchhoff's voltage law. This says that the sum of all voltage drops around any closed loop must be zero. So here's a little circuit example. We have a couple resistors and a voltage source. And if we work our way around the loop, V2, that's the voltage here, and that's negative because of the polarity that we've assigned. So minus is here, plus is here. So we're going minus to plus. That means it's negative voltage. Plus V3, because V3 we're going from plus to minus, and V1, again, plus to minus. So minus V2 plus V3 plus V1 equals 0. A couple of other important equations. So these are for reactive components. So an inductor, the relationship between voltage and current, V equals L di dt. So the change in current with respect to time multiplied by the inductance value will give you the voltage that shows up across the inductor. And the voltage is from plus to minus. Another way to formulate this is that the change in current with respect to time is V divided by L. For the capacitor, that's kind of the counterpart to an inductor, I equals C dV dt. And if we remember that hot plug example where the current went through the roof when we hot connected it, this equation is why. The voltage changed by 12 volts in 10 microseconds. So that means dV dt is a big number, and multiply it times C and the current. C is a constant, but if dV dt is large, I is going to be large. And that's why that current surge happened when we plugged in a live voltage into a discharge capacitor. So these are equations that I use every day for doing power design. So it's important to get comfortable with those. Just a couple more fundamentals. Conservation of power. The input power is defined by V in times I in. So the input voltage times the current that we're drawing out of it, that's how much power is being delivered. That's the input power. The output power, V out times I out. And the power loss is the difference between these. So we put 10 watts into the system and our output only delivers 9 watts. That means we're losing a watt someplace. And that'll be important as we look at the different types of power converters. Efficiency is another way of looking at conservation of power. The efficiency is power out divided by power in. And because we live in the real world, the efficiency is always less than 100%. Laws of thermodynamics say that there's no ideal conversion. Maximum efficiency is driven by device physics. So the resistance in various parts of the circuit will cause power dissipation. And the different devices that we use determine what those levels are. So that's all I have for today. Thank you all for attending.